Today, we're diving into something really cool. It's a field all about unlocking the wisdom that's hiding in data we already have. It's called offline reinforcement learning, and it's basically teaching machines how to make smarter decisions by just studying the past, without all the risk of real-world trial and error.
So let's kick this off with a pretty big question. Imagine a self-driving car. What if, instead of having to learn by making scary, potentially dangerous mistakes on the road, it could just tap into a massive library of every single turn, every merge, every sudden stop ever made by millions of human drivers? That, right there, is the core promise of offline RL. So what's the big difference here? Well, think of it like this. Traditional reinforcement learning, the online kind, is all about learning by doing. An AI agent goes out, tries stuff, gets feedback, and slowly gets better. It's an active, hands-on process. Offline RL, though, is more like learning from a textbook. The agent gets a fixed data set, that's its textbook, and it has to learn everything it possibly can from that material alone, without ever getting to go out and try things for itself. But you might be thinking, why would we want to do that? Why tie our agents' hands? Why learn from a fixed textbook when you could just go explore the world? Well, as it turns out, there are some really good reasons. The biggest one, safety. It's absolutely critical. You just can't have a surgical robot or a self-driving car learning on the job when a single mistake could be, catastrophic. And second, we are literally swimming in data. Just think about all those driving logs, medical records, or even data from old robot experiments. It would be a huge waste not to use it. And finally, it's just plain efficient. Collecting new data in the real world, especially with physical robots, is incredibly slow and super expensive. Offline RL lets us reuse the data we have over and over again.
Okay, so to really get how this works, there's one key term you gotta know: the behavior policy. This is basically the policy, or more likely a whole mix of policies, that created our data set in the first place. So if our data comes from a bunch of human drivers, the behavior policy is just the sum of all their driving styles: the good, the bad, and the ugly. We don't know exactly what this policy is, but we have all the data it spat out.
Now, this all sounds great, right? Just take an algorithm we already have, feed it all this offline data, and we're done. Well, not so fast. This is where we run smack into the central villain of our story, the overestimation trap.
The problem has a name. It's called distribution shift. See, our data comes from one place, that behavior policy, but we want to learn a new policy that's going to act differently and hopefully a lot better. The moment our new policy starts thinking about an action that wasn't very common in the original data, things can go sideways fast.
So let me walk you through how this trap gets sprung. The algorithm's value function, the part that estimates how good an action is, learns from what it sees in the data. But for actions it's never seen before, like, a bizarre U-turn on the highway, it has no clue. Its estimate for that is basically just random noise left over from when it was initialized. And just by chance, some of this random noise is going to be a really high number, making a terrible action look like a brilliant move. The policy then grabs onto this fantasy action, and here's the key: because it's offline, it can never actually try it to find out it was a horrible idea. It gets stuck in its own little fantasy world.
And this visualizes the problem perfectly. The actions that were actually in the data have these reasonable learned values. But look at that out-of-data action. Its value is way up there, not because it's a good move, but purely by random chance. Any standard algorithm will greedily pick that action, thinking it's found some amazing shortcut, when really it's about to drive right off a cliff. So how on earth do we stop this from happening?
Well, the first family of solutions isn't about trying to find some wild, brand new strategy. Instead, it's all about becoming a much smarter imitator of the data we already have. And what's really fascinating here is that offline RL can do something way more powerful than just copying the best single drive in the whole dataset. It can actually learn to stitch together the best parts of many different, not-so-great drives. Okay, picture this. In our dataset, we have trajectory A. A car merges onto the highway perfectly. It's a beautiful sequence of actions. But then, it completely misses its exit and gets stuck in traffic. So a great start, but a terrible finish.
Now let's look at another one, trajectory B. This car botches the merge, cuts someone off, just a total mess. But then it nails the exit perfectly and gets to its destination right on time. A bad start, but a fantastic finish.
So a simple imitation algorithm might just average these two out, and you'd get a mediocre policy. But a good offline RL algorithm can learn to take the perfect merge from trajectory A and combine it with the perfect exit from trajectory B.
It creates a completely new optimal path that is better than anything that ever actually happened in the original data. That right there is the magic of stitching.
So how do we actually do this stitching? Well, one of the first really successful methods is called advantage-weighted regression, or AWR. The idea is actually pretty intuitive. It's basically imitation learning, but instead of copying every action equally, it weights them. It pays way more attention to actions that led to a better-than-average outcome, it upweights them, and it pretty much ignores the actions that led to worse outcomes.
So think back to that moment on the highway ramp where one car merged well and the other merged poorly. AWR sees that the good merge led to a much better result. It had a high advantage. So it cranks up the dial on copying that good merge and turns the volume way down on the bad one. That's the exact mechanism that lets it stitch together the best parts of different behaviors.
AWR is a huge step in the right direction, but it's got a limitation. It's still making decisions based on the value of that original, kind of messy behavior policy. So the question is, can we do even better? Can we learn a value function for an optimal policy directly from that same offline data?
And this is the key question that really pushes us toward more advanced methods. I mean, AWR is weighting actions based on how good they were for the original drivers. But what if we could learn a value function that represents a policy that's already better than any of those drivers, just by looking at the data they left behind? And that brings us to an algorithm called implicit Q-learning, or IQL. IQL uses this really clever mathematical trick called expectile regression. What this does is it allows it to learn a value function that is optimistic by its very design. So instead of valuing states based on the average thing that happened in the data, it focuses on the better things that happened, all while staying safely grounded in actions it has actually seen before. No more fantasy land. Yeah, what's so cool here is the difference in philosophy. A standard algorithm, it uses a symmetrical loss. It hates overestimating a value just as much as it hates underestimating it, so it always settles right in the middle, on the average. Expectile regression, though, it uses an asymmetric loss. It penalizes underestimation way more than overestimation. This literally pushes the value estimate upwards, not to some random high number, but towards, say, the 70th or 80th percentile of the actual outcomes we saw in the data. It learns to be optimistic, but in a realistic way. Okay, let's bring this all home. We've seen the core problem of learning from the past, this overestimation trap, and we've looked at some incredibly clever ways to get around it. So, let's just quickly recap the journey here. We started with the simplest idea, filtered imitation, just copy the best stuff. But the problem is it throws away tons of useful data and it can't stitch. Then we moved to AWR, which cleverly copies all the data but just weights the good actions higher. This lets it stitch, but it's still kind of stuck thinking about the value of the original messy policy. And finally, we have IQL, which uses that awesome optimistic expertile regression to learn a much better value function directly, allowing it to find even better policies. So if there's one thing to take away, it's this. Offline RL isn't just about learning from the past. It's a powerful way to turn giant, static piles of data into actionable intelligence. By safely keeping the learning constrained to what it actually knows, it avoids those dangerous fantasies. And by cleverly stitching together the fragmented wisdom in our data, it can synthesize a better future from everything we've already done. And that leaves us with one final big thought. I mean, from medicine to finance to robotics, we have collected absolute mountains of data over the decades. As these offline RL methods get even better, what seemingly impossible problems are we going to be able to solve by finally, truly unlocking the hidden potential of our own past?